Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the deepest questions of all. Does space end? Is there a boundary, a wall, a final edge to everything? Or is the universe more like an endless ocean, stretching beyond every horizon we can ever hope to see? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into space together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. So does space end? To even approach the question, we have to tread gently. Our everyday experience whispers that everything must have a boundary. The road ends. The sea meets the shore. Even a balloon has a surface where the inside stops and the outside begins. But the universe, as we'll see, is not an everyday kind of place. It plays by rules that stretch and bend our imagination. When you hear the word space, perhaps you imagine a black canvas dotted with stars, a kind of stage where galaxies dance. For Newton, centuries ago, space really was thought of as exactly that, a great stage, absolute and unchanging, on which matter performed its endless play. To him, space existed independently, like the floor beneath your feet, whether or not anyone was standing on it. But Einstein came along and tugged gently at that picture. He suggested that space is not a rigid floor, but a flexible fabric that can bend, stretch, and even ripple. It's a living participant in the cosmic story, not just the background. If you've ever placed a heavy ball on a trampoline and watched the fabric dip and curve, you've seen a playful version of what Einstein meant. Space itself curves in response to mass and energy, and that's only the beginning. What looks like empty space is not empty at all. Physicists tell us that it seethes quietly with quantum fields, flickering particles that appear and vanish faster than you can blink. Even the vacuum has a kind of gentle hum to it, a background temperature just a few degrees above absolute zero. The faint glow of the cosmic microwave background, the after echo of the Big Bang. So when we ask, does space end? We are not simply asking whether there is a final brick wall somewhere out there. We are asking something subtler. We are asking whether this flexible, rippling, softly humming fabric can have an edge at all. The mind loves to imagine a boundary. Children run to the end of the street and ask what lies beyond. Sailors once wondered if the sea itself had cliffs at its margins. Our ancestors in every age have looked up at the stars and thought, perhaps there is a dome, perhaps there is a curtain, perhaps the universe is wrapped in a great shell. The question is old, and it carries with it that same restless mixture of curiosity and unease. But when we shift our gaze from imagination to observation, the universe answers with subtleties rather than blunt edges. What we see is an observable universe, a bubble defined not by walls but by time and light. Light takes time to travel, and the universe has only existed for a finite time, around 13.8 billion years. That means there is only so far light could have travelled since the beginning. That distance defines the horizon of what we can see. Beyond it, not because of a wall, but because light has not yet had the chance to reach us, there are regions hidden forever from our sight. This horizon is not like the end of a road, but like the horizon at sea. When you stand on a beach, the ocean seems to stop at the line where the sky meets the water. But sail out far enough, and you find that the sea continues, stretching and curving away. The horizon is only a limit of your vision, not of the ocean itself. In the same way, when we ask, does space end? Science gently whispers back, there may be a limit to what we can observe, but that does not mean there is a literal edge. The observable universe has a radius of about 46 billion light years. That number sounds impossibly large, but it's important to soften it. 1 light year is simply the distance light travels in a year. Imagine the warm glow of a candle across a room. That light takes only a fraction of a second to reach you. Now imagine that glow travelling not across a room, but for an entire year, covering nearly 10 trillion kilometres, and you begin to sense the vastness hidden in even a single light year. Multiply that by 46 billion, and you are brushing against the scale of what we can see. And yet, that is only what we can see. The universe may extend much farther, perhaps infinitely farther, or perhaps it curves back on itself in a way we have not yet fully measured, like the surface of a sphere where you can walk forever without ever finding an edge. The key is to hold gently in mind that end is not a simple word here. There may be observational ends, like horizons, defined by the age of the cosmos and the speed of light. There may be mathematical ends, like boundaries in certain speculative models. But when it comes to physical ends, walls, cliffs, sharp cutoffs, the universe seems to politely refuse. It offers horizons instead of fences, expansions instead of edges, mysteries instead of closures. As we drift further into the story, we will follow these horizons more closely. We'll listen to what the cosmic microwave background tells us about the early universe. We'll explore how the geometry of space can be finite and boundless at the same time, and we'll gently peek into the speculative gardens of multiverse theories, holographic ideas, and cosmic fates. For now, let the thoughts settle like a feather. Space does not end in the way streets or walls end. It may not end at all. What we meet instead is the horizon of our own sight, the boundary of our own reach, and the soft invitation to wonder what lies beyond. When people first began to think seriously about what space actually is, they often pictured it as something simple and absolute, a giant container in which the universe lives. To Sir Isaac Newton in the 17th century, space was an invisible stage stretched endlessly in every direction. It was unchanging, unaffected by the actors who walked upon it. Matter and motion played out on this stage, but the stage itself never shifted, never bent, never responded. This picture is comfortable in many ways. It matches our intuition. When you set a chair, in a room the chair doesn't bend the floor beneath it. When you run across a field, the air does not warp to hold you. Newton's idea made the universe feel straightforward. Space was simply there, an infinite backdrop, permanent and solid even if no one was looking. But science rarely leaves comfortable ideas untouched for long. Centuries later, Albert Einstein would arrive with a theory that shook this stage until it dissolved entirely. He suggested that space is not a silent floor, but a flexible fabric, woven together with time into something called space-time. And this fabric could bend, stretch, and ripple in response to the presence of matter and energy. How can something as abstract as space bend? A helpful image is the trampoline. Picture its stretched surface smooth and flat. Place a bowling ball in the centre, and the fabric dips into a curve. Now, if you roll a marble across the surface, the marble spirals inward toward the heavier ball, not because the larger ball is pulling it with an invisible string, but because the fabric beneath it is curved. The marble is simply following the shape of the surface. In Einstein's vision, planets orbit stars for the same reason. Earth circles the sun not because of a mysterious invisible force tugging it, but because the sun bends the fabric of space-time around it. Earth follows the straightest possible path in that curved geometry. Physicists call this path a geodesic, but you can imagine it more gently as the natural line, traced by anything moving through a curved landscape. This was a profound shift. Newton had taught that gravity was a force between objects. Einstein reframed it as geometry itself. Where Newton imagined the universe as actors moving across an untouched stage, Einstein revealed that the stage can twist and turn, reshaping the dance entirely. If we translate this into everyday life, the effect is almost invisible yet deeply real. When you drop a mug and it shatters on the floor, you're seeing space-time's curvature in action. When the moon circles the Earth and tides rise and fall on the shore, you're watching the play of a fabric too vast to touch, but too important to ignore. And there is more. Because time is bound to space, gravity affects not just motion, but also the flow of time itself. Clocks run more slowly in stronger gravity. That means the watch on your wrist, if you stood at the bottom of a deep valley, would tick just a little slower than an identical watch high on a mountain. The difference is tiny, fractions of a second across many years, but it has been measured. In fact, the satellites that guide your GPS must correct for this effect. Without Einstein's insight, your phone's map would place you blocks away from your actual location. Einstein's view also allows for ripples in space-time, known as gravitational waves. When massive objects like black holes collide, they send out shivers in the fabric itself. In 2015, scientists recorded such: a ripple arriving at Earth, a faint stretching and squeezing smaller than the width of a proton, yet unmistakable. In that moment, we heard space-time sing. So space, in Einstein's universe, is not an empty box. It is a participant, a dynamic stage that responds to every mass and every flash of energy. When we talk about whether space ends, we must remember we are asking about this flexible fabric, not a simple container. We are asking about a geometry that can bend and ripple, a living backdrop rather than a silent void. And even when we call space empty, it resists the name. Quantum physics tells us that fields saturate every inch of it, and tiny particles flicker in and out like fireflies, appearing and vanishing in the dusk. The vacuum is restless, filled with energy we cannot see, but can sometimes measure in delicate ways. One famous effect, called the Casimir effect, shows that even nothing can exert a push when two metal plates are placed very close together. The vacuum between them shifts subtly, and the plates are drawn together as if space itself were whispering between them. To imagine this more softly, think of the air in your room at night. You cannot see it, but you know it is there. It carries warmth, scents, and the faint hum of sound. Space, too, carries invisible ingredients. Not air, but fields and fluctuations. A background temperature of about 2.7 degrees above absolute zero. The faint afterglow of the Big Bang stretched across the entire sky. All of this reshapes the way we ask the question, does space end? If space is a dynamic fabric, woven with energy and time, the idea of a hard boundary becomes stranger. A trampoline surface doesn't end with a cliff. It connects to its frame. A balloon doesn't end with an edge. Its surface curves smoothly back into itself. Space, in Einstein's view, is not so much a place with borders as a shape to be understood. And yet, despite these discoveries, our everyday senses cling to Newton's simpler picture. When we look up at the night sky, it still feels like a stage. The stars seem fixed against a dark background, twinkling but unmoving. The flexibility of space-time is subtle, quiet, easy to overlook in the rhythm of daily life. But that is the joy of science. It reveals what lies behind appearances. It shows us that even when nothing seems to be happening, the fabric beneath our feet is alive with curvature, ripple, and whisper. The universe does not rest on a rigid foundation. It floats, bends and hums on a stage that is itself a character in the cosmic story. If we follow the thread a little further, this brings us to another question. What limits our sight of this fabric? If space bends and stretches without obvious boundaries, what defines the bubble of universe we can actually observe? To approach that, we must step gently into the concept of horizons. Not walls, not fences, but limits shaped by light and time. If you step outside on a clear night and gaze upward, the darkness between the stars might feel like the purest emptiness you could imagine. Nothingness stretched across the sky, yet science, with its careful eyes, has discovered that this darkness is not truly empty. It is filled with subtle presences, quiet energies, and faint whispers of the cosmos. Space, even in its most silent corners, is alive with hidden ingredients. One of the most surprising lessons of modern physics is that what we call a vacuum is not simply nothing. In Newton's time, a vacuum was imagined as a void, a clean slate with no particles at all. But quantum physics reshaped this picture. It showed that even in the absence of matter, fields remain. They shimmer everywhere, permeating the universe like invisible threads woven into the cosmic fabric. Imagine standing in a meadow in late summer. At first glance, the field might look still, the grass unmoving. But if you crouch low, you notice insects darting, breezes stirring, seeds floating on invisible currents. What looked empty is actually restless. The quantum vacuum is like that meadow. Tiny particles flicker into existence and vanish again in an instant. They are called virtual particles, but their effects are real. These restless fluctuations can even push and pull. One delicate experiment reveals this clearly. If you place two metal plates extremely close together in a vacuum, they are nudged toward each other by the surrounding quantum fields. The vacuum between the plates is ever so slightly different from the vacuum outside, creating a pressure. This is called the Casimir effect, named after the physicist who first described it. To us, it feels like a reminder. Even nothing has texture. Space also carries a faint warmth of its own. When scientists tune their instruments to look past stars and galaxies, what they find is a background glow filling the entire sky. It comes from every direction, perfectly even, like a gentle mist of microwaves. This glow is the cosmic microwave background, the afterglow of the Big Bang itself. Today, it is cold, about 2.7 degrees above absolute zero, which is just a hair above the coldest possible temperature. But billions of years ago, it was much hotter, blazing across the infinite cosmos. This background is not just a leftover, it is a kind of memory, a photograph of the universe when it was only 380,000 years old. Before that time, space was filled with light that could not travel freely. It scattered constantly off particles as though the cosmos were wrapped in fog. When the universe cooled enough for atoms to form, the fog lifted and light streamed freely. That ancient light has been travelling ever since, stretched by the expansion of space, softened into the faint microwave glow we see today. So when you look into darkness, you are not staring into nothingness. You're looking into a sea of subtle energies, hidden fluctuations, and the faint after-echo of creation itself. Empty space is more like a quiet symphony than a blank silence. Even gravity leaves its fingerprints in this emptiness. Recall Einstein's idea of space-time as a fabric. Just as a trampoline can dip and ripple, so can space itself. When massive objects collide, say two black holes spiraling together, they send out shivers in space-time. These are gravitational waves, ripples in the very fabric of the cosmos. They race outward at the speed of light, stretching and squeezing everything they pass through. For decades, these waves were predicted but never heard. Then, in 2015, scientists recorded the faint signal of two black holes colliding over 1 billion light-years away. The wave that reached Earth changed the length of a measuring device by less than the width of a single proton. Yet, it was enough. Space itself had carried us the news of a cosmic embrace. If you want an everyday anchor for these hidden energies, think of the air in your room at night. When you breathe in, it feels invisible, weightless, almost absent. But strike a note on a guitar or hum a tune, and suddenly the air is alive, carrying waves of sound. Space too carries waves, though they are far gentler and stranger than sound. Sometimes they are ripples of gravity, sometimes they are flickers of virtual particles, sometimes they are the afterglow of the Big Bang. And beyond all this is another mystery: dark energy. This is not just vacuum buzzing quietly. It is something even stranger, a pressure within space itself that drives the universe to expand faster and faster. We will return to it in more detail later, but it is worth noting here. What appears empty may actually hold the key to the fate of the cosmos. To make this less abstract, imagine baking a loaf of raisin bread. As the dough rises, the raisins move apart. There is no wind pushing them, no invisible strings pulling. It is the dough itself that stretches, carrying them away from each other. In the universe, galaxies are like raisins, and space is the dough. And this dough is not passive. It is swelling faster and faster, pushed outward by dark energy. The emptiness between galaxies is what carries them apart. So we return to our question: does space end? If space were truly empty, we might imagine its edges like the edge of a table, a clean break between something and nothing. But space is never truly empty. It hums with quantum fields. It glows with the after-echo of the Big Bang. It ripples when massive objects collide, and it swells with a push of dark energy. A stage so restless does not end like a floorboard. It flows, it stretches, it changes. And yet, this fullness of emptiness also carries limits. We cannot see past the horizon of the observable universe, because light has not had time to reach us. We cannot directly grasp what lies beyond our cosmic bubble. But what we can say, with some comfort, is that the darkness between the stars is not barren. It is alive with the quiet breath of the universe. If we follow the trail of clues a little further, we find ourselves asking, how far does this cosmic bubble extend? How large is the region we can observe, and why does that horizon exist at all? To answer, we need to step gently into the idea of the observable universe, a concept that turns light into a kind of cosmic ruler, stretching across billions of years. When we ask whether space ends, one of the most natural places to start is with the idea of the observable universe. This phrase sounds technical, but the idea is gentle. It simply refers to the bubble of space, from which light has had time to reach us since the beginning of the cosmos. Imagine holding a lantern in the dark. Its glow spreads outward. Farther away, the light is dimmer, but still present. Now reverse the thought. We are not the lantern, we are the observers. Light from distant places has been travelling toward us for billions of years, and the furthest light that has had enough time to arrive defines the horizon of what we can see. This horizon is not a wall. It is not painted in sharp colours like the end of a map. It is more like the horizon you see at the ocean. When you stand on the shore, the sea appears to end where it meets the sky, a curved line in the distance. But if you sail toward that line, the horizon does not get closer. It stays always at the same distance, simply revealing more ocean as you go. The observable universe is like that sea horizon. It marks the limit of what we can see from our vantage point in space and time, not the edge of the cosmos itself. The scale of this horizon is staggering. Our universe has existed for around 13.8 billion years. You might think that means the observable radius should also be about 13.8 billion light years. After all, light travels 1 light year in a year. But here's the twist. While light has been on its way, space itself has been expanding, stretching the journey. Imagine trying to walk across an airport-moving walkway that is itself extending under your feet as you move. No matter how far you walk, the floor keeps pulling more distance into existence. For this reason, the actual observable radius is not 13 billion light years, but closer to 46 billion light years. That means the full observable universe is about 93 billion light years across. These numbers are so large they are hard to picture. A single light year, the distance light travels in 1 year, is nearly 10 trillion kilometers. To soften that, imagine driving a car at highway speed, say 100 kilometers per hour. At that pace, it would take you over 100 billion years to travel just 1 light year. Multiply that by 46 billion, and you glimpse how vast this cosmic bubble is. The mind cannot truly hold it, but that is all right. The important point is that the horizon exists, and it is far, larger than our first instincts might suggest. The horizon also teaches us something beautiful. Looking far means looking back. When you look at the moon, you see it as it was about 1 second ago, because light takes a second to arrive. The sun, when it shines on your face, is already 8 minutes old. The nearest star beyond the sun beams at us from more than 4 years in the past, and the galaxies at the edge of our observable bubble glow from billions of years ago, long before Earth even formed. This means the observable universe is not simply a sphere of distance, it is also a sphere of time. Each layer we see is like a page in a history book. The farther out we look, the further back in time we are reading. The horizon at 46 billion light years corresponds to a time when the universe was just beginning to lift its primordial fog. But this observable sphere is not the same for every observer. Imagine two people standing on opposite sides of Earth, each gazing outward. Their horizons overlap but are not identical. Each person sees a slightly different cosmic bubble centered on themselves. Expand that thought. Every galaxy, every star, every point in space has its own observable universe, its own horizon. From the perspective of an alien astronomer on a distant world, the edge of the cosmos would be in a different place than it is for us. This is a subtle reminder. The observable universe is a relationship, not a fixed structure. It depends on where you are and when you look. The cosmos itself may extend much farther, perhaps infinitely farther, beyond any one observer's horizon. You might ask, if the observable universe is defined by light's travel time, is there any way to peek beyond it? The answer is no, at least not directly. Light is our primary messenger. We cannot yet receive signals from regions where the journey has taken longer than the age of the cosmos itself. These places are not hidden by walls, but by time. They are simply too far for their messages to have arrived. Think again of standing on a hill at dawn. The land around you begins to brighten, but the valleys far away remain in shadow. They are not missing. They are just waiting for the sunlight to reach them. In the same way, there may be galaxies, clusters, and vast regions of space far beyond our horizon. They are not absent. They are simply waiting beyond the reach of our light. Scientists use this horizon not only as a measure of distance, but also as a tool. By studying the faint glow of the cosmic microwave background, the light released when the universe was only a few 100,000 years old, they can read subtle patterns that reveal the curvature of space and its composition. The observable universe is not just a limit, it is a lens, a way of studying what came before us. The idea of a horizon can feel frustrating. It means we cannot know everything. But it also carries a kind of comfort. Just as the ocean horizon invites sailors to dream of what lies beyond, the cosmic horizon invites us to imagine the unseen. It whispers that our bubble is not all that exists. It hints at expanses beyond our reach, perhaps forever beyond. From here, the story opens into something even more curious. The fact that there is more than one kind of horizon. The particle horizon marks the furthest light we can see today, but there is also another boundary, subtler, called the event horizon, which marks the limits of what light will ever reach us in the future, even if we wait forever. Our quiet exploration now turns to that distinction, where the difference between seen and never to be seen comes into focus. If we let our minds drift further into the question of cosmic limits, we find that there is not just one horizon, but several, each with its own quiet story to tell. The first is the particle horizon, the furthest distance from which light has had time to reach us since the birth of the universe. We touched on this already, when we said that the observable bubble has a radius of about 46 billion light years. That distance is set by the age of the cosmos, 13.8 billion years, stretched by the expansion of space itself. The particle horizon marks the outer rim of what we can see today, a gentle line in time as much as in space. But there is another horizon, stranger and perhaps more haunting, the cosmic event horizon. It sounds like something pulled from a dream or a science fiction tale, but it is a simple idea once softened. While the particle horizon is about what we can see right now, the event horizon is about what we will never see, no matter how long we wait. Here's the reason. The universe is not just expanding, it is expanding faster and faster, pushed outward by what we call dark energy. Imagine standing on a beach with friends, each of you walking into the water at the same time. At first, even as the waves carry you apart, you can still shout and hear one another. But if the tide begins rushing out more and more quickly, there comes a point when your voices can no longer carry across the widening gap. No matter how loudly you call, the distance grows too fast. That is what the event horizon means for galaxies. Some of them are already receding so quickly that even though light leaves them now, that light will never bridge the swelling space to reach us. In everyday terms, this is like watching a loved one walk away down a long road that is itself stretching under their feet. You can see them for a while, but you know there will come a moment when they slip beyond earshot forever. They do not vanish behind a wall, and the road does not end. The separation simply becomes permanent. The event horizon of our universe today lies at about 16 billion light-years. Any galaxy beyond that line, though perhaps still visible from ancient light it sent long ago, is lost to us in terms of future communication. We can never receive new messages from it. The photons it sends out today will never arrive, because the expansion of space pulls the distance wider too quickly. This creates an interesting contrast. Some galaxies are visible in our telescopes right now, because we are seeing the ancient light they emitted billions of years ago. But those same galaxies are already beyond the event horizon. They are like actors whose performance reaches us on delay, the recording of a play that ended long ago. We can watch the light that left them in the past, but we will never see their present or their future. They are permanently beyond contact. In poetic terms, the particle horizon tells us how far our eyes can reach back in time, while the event horizon tells us how far our hands can reach forward. One is the memory of what has already arrived, the other the promise, or rather the refusal, of what will never arrive. The existence of these two horizons teaches us something subtle about the universe. Limits are not always physical walls, but relationships between light, time, and expansion. The sky is filled with galaxies whose fates differ only by distance. Those closer than 16 billion light-years can still share their future with us. Those farther away cannot. The line is not painted anywhere, but it is real, defined by the steady arithmetic of cosmic growth. If we think of the observable universe as a great cosmic play, then the particle horizon is the curtain that hides all the acts that have not yet had time to reach us. The event horizon is a quieter curtain. It hides the scenes that will never reach us, no matter how patiently we wait. Between the two lies our stage, filled with the actors and galaxies that can still touch us with their light. This might sound melancholy. To know that most of the universe is slipping beyond reach can feel like watching sand pour through an hourglass. But there is also beauty here. It means the light we do see, the galaxies, the clusters, the faint glow of the background, is precious. Each photon that reaches our telescopes has won a race against expansion, travelling billions of years to arrive at our corner of the cosmos. Each is a survivor, carrying the story of a place we may never contact again. You can picture it like messages in bottles washing up on a shore. Some bottles come from nearby islands and you may hope to write back. Others drift from continents too far away, lands whose shores you will never see. You can still read their words, treasure their stories, and know that they exist, even if the tide never allows a reply. The concept of horizons also reshapes the way we think about time. For nearby galaxies, we share a kind of mutual future. Light and perhaps even visits, imaginary for now, could pass between us if civilizations ever arose and endured. For those beyond the event horizon, there is no mutual future, only a shared past. We are forever linked by the light of what once was, but never by what will be. And so we return to our guiding question. Does space end? Horizon suggests a different answer. Space does not end, but our reach does. The universe places a gentle hand on our shoulder and says, "You may look this far, but no further. You may listen to echoes from that star, but no new voice will ever arrive. From here, the path now carries us toward a deeper reflection. What does it mean to see the past written in light?" If every look at the night sky is also a look backward in time, then our horizons are not just distances, but windows into history. Our quiet exploration now turns to the idea of telescopes as time machines, instruments that allow us to read the story of the universe across billions of years. When you look up at the night sky, it's easy to imagine that you're seeing the universe as it is right now. The stars twinkle, the moon glows, and distant galaxies shimmer faintly like lanterns in the dark. But in truth, every glance upward is also a glance backward. Light does not arrive instantly. It travels at a steady pace, about 300,000 kilometers every second. And because distances in the cosmos are so vast, that steady pace translates into long delays. The moon, so close in cosmic terms, already shows us the past. Its pale light takes a little more than 1 second to cross the space between it and Earth. When you look at the moon, you're looking at it as it was 1 second ago. The sun is further away, and sunlight takes about 8 minutes to reach us. Every sunrise is therefore a glimpse of the sun's past. Stretch that idea outward, and the nearest star beyond the sun is over 4 years away, meaning its light shows us an image from 4 years earlier. Our telescopes, those quiet eyes of glass and metal, extend this principle to staggering extremes. They collect light that has been travelling not for minutes or years, but for billions of years. In other words, telescopes are time machines. They allow us to see galaxies not as they are now, but as they were when the universe was young. Each observation is a postcard from the past, delivered across unimaginable distances. This idea can feel abstract until we soften it with a simple anchor. Imagine finding a box of old photographs in your attic. You flip through faded snapshots of grandparents as children, parents on their first day of school, your own baby pictures. None of these images show the people as they are today. They capture them as they were, frozen in time. Telescopes do the same with galaxies. Every picture is an old photograph, some billions of years out of date. And unlike photographs in a box, these cosmic snapshots have been in motion the entire time. As light leaves a galaxy, space itself stretches. The wavelengths of light are pulled longer by the expansion of the universe, shifting the glow of galaxies toward the red end of the spectrum. This is called cosmological redshift. In gentler words, it is like hearing a siren as an ambulance drives away. The sound stretches, the pitch drops. With light, the expansion of space itself stretches the wave, softening its colour. Astronomers measure this redshift as a kind of cosmic clock. The more stretched the light is, the longer it has travelled, and the further back in time we are peering. In this way, the colours of galaxies become records of their journeys, quiet testimonies to how far and how long the light has travelled to reach us. Through this lens, the universe becomes a layered archive of time. Nearby galaxies, their light shifted only a little, appear as they were relatively recently. Farther ones show us earlier chapters, when the cosmos was more youthful and raw. The most distant galaxies reveal a time when stars had only just begun to gather into clusters, when the universe was still messy, clumpy, and unrefined. Our instruments have now reached so far that we can see almost to the dawn itself, the time when the first galaxies were assembling from clouds of hydrogen and helium. That light has travelled more than 13 billion years. To frame this gently, if you could hold that beam of light in your hands and trace its journey, it would have passed by countless galaxies, dodged merging clusters, and sailed across a sea of expanding space, only to end its voyage quietly in the lens of a telescope on Earth. The thought is both humbling and comforting. Each faint photon we capture has survived a journey across nearly the entire history of the universe. When we collect those photons and form them into an image, we are reading letters written billions of years ago, messages from a time when Earth itself did not yet exist. Think of an old letter arriving at your home long after it was written. The paper may be worn, the ink faded, yet the words still carry meaning. They carry a voice from another time. The light from distant galaxies is like that. It speaks softly of a universe that has long since changed, but the memory remains intact. In this way, telescopes let us watch cosmic history unfold, not in real time, but in a patient unfolding of the past. Each deeper look takes us further back. Each red-shifted spectrum is a clue, like an archaeologist brushing dust from an ancient artifact. And the wonder is that we do not need to leave our planet to do this. With the right mirrors and lenses, with careful patience, the sky itself delivers the past to us. This also means that when you gaze at the stars, you are never simply seeing now. The night sky is a collage of times. Some of the stars you see tonight may already have burned out, their final light still on its way to Earth. Some of the galaxies may now look very different than they do in our telescopes, but we cannot yet know. The sky is a patchwork quilt of yesterdays, layered into a single view. Rather than making the cosmos feel distant, this truth can make it feel intimate. We live surrounded by the memories of the universe, written in light. The stars above are not only far away in space, they are far away in time, and yet they share those memories with us freely, without asking anything in return. As we drift further into this story, we begin to see that these snapshots of the past can be organized, much like the rings in a tree or the pages of a family album. Galaxies at different distances show us different ages of the cosmos. Taken together, they form a living history book, one we can read page by page across billions of years. The trail of clues leads us gently into the idea of deep time and cosmic history, where the universe itself becomes a layered record of its own growth. When we peer through telescopes and gather light that has travelled across billions of years, we're not just seeing single snapshots, we're watching the universe's life story unfold in layers. Each distance, each galaxy, is a window into a different age. Taken together, these views form a kind of cosmic album, a set of pages we can flip through to see how the universe has grown and changed across time. A simple way to imagine this is with the rings of a tree. When you cut across its trunk, you see concentric circles. The inner rings mark the years when the tree was young, the outer rings its more recent growth. Each layer records a season, a climate, a piece of history. The cosmos is like that. The galaxies closest to us are the outer rings. They show the recent universe. The more distant galaxies are the inner rings. They show us what the cosmos looked like when it was still young. Another gentle picture is the family photo album. Flip through, and you see images of grandparents as children, parents as teenagers, yourself as a baby. The people are the same, but they change across the pages. Faces grow older, clothes shift in style, settings transform. In much the same way, the universe presents us with snapshots of itself at different ages. What do these snapshots reveal? Nearby galaxies, the ones only millions of light years away, look mature and well organized. They are the spirals and ellipticals that decorate astronomy textbooks. Pinwheel arms curling with stars, glowing cores that host billions of suns. These galaxies are like the grown adults in the family album, formed and settled, their structure graceful and familiar. Look farther, and the galaxies change. Billions of light years out, we see younger versions. They are smaller, messier, often distorted. Many are clumps rather than grand spirals, their stars still gathering into order. These are the cosmic toddlers and teenagers, awkward and unfinished, yet full of energy. Some collide and merge, their shapes twisted by gravity, like siblings wrestling in the yard. At the farthest reaches, beyond 13 billion years, we glimpse the universe's infancy. Galaxies there are little more than flickers, faint smudges of light caught by the most powerful telescopes. These are the newborns, collections of stars just beginning to ignite, out of primordial gas. They remind us that the universe has not always looked as it does now. What seems eternal, the great galaxies wheeling across the sky, is actually the product of a long, restless growth. This growth is written not only in the galaxies themselves, but in the light we capture from them. Young galaxies shine with bluer light, the glow of hot new stars burning fiercely. Older galaxies lean toward warmer, redder light, the glow of mature suns that have burned steadily for billions of years. To astronomers, these colours are like the shades of leaves in a forest, telling the seasons of cosmic time. The great advantage of light's delay is that we do not need to guess at this story. We can see it. We do not have only one frozen page, we have an entire library. Each galaxy at each distance is a chapter. Together, they let us reconstruct the narrative of cosmic history, from a hot, dense beginning, to the first stars, to galaxies merging and growing, to the vast web of clusters and filaments that lace the universe today. And this story is still unfolding. When we look at the sky tonight, we are seeing not only what has already happened, but also the trajectory of what is still to come. The galaxies we view in their youth are continuing to evolve, even though their present light has not yet reached us. Somewhere, billions of light years away, those galaxies exist right now in forms we cannot yet see. Older, perhaps larger, perhaps stranger. It is like waiting for a letter from a distant friend. You know they continue to live their life even though the news has not arrived. Deep time is not easy for the human mind to hold. We measure our days in hours, our years in birthdays, our generations in centuries. 1,000 years feels enormous, 1,000,000 nearly ungraspable, but 1,000,000,000 years, let alone 13 or more, is almost beyond imagination. That is where the gentle metaphors help. Tree rings, albums, letters in the mail. They let us approach scales of time without feeling overwhelmed. And yet, even if we cannot hold the full scale, we can sense its shape. The universe is a story with a beginning, a middle, and a future still unwritten. By studying galaxies at different distances, we step into that story. We become readers of a book that writes itself in starlight. There is something comforting in knowing that the night sky is layered with ages. It means that when you look up, you are not just seeing a scattered pattern of stars, you are looking through time itself. The Milky Way band arching across the sky is an ancient diary, written one photon at a time, waiting for eyes to read it. And perhaps there is another quiet comfort. We are part of this story too. Our sun formed about 4.5 billion years ago, in a universe already bustling with galaxies. The atoms in your body were forged in stars that lived and died long before Earth was born. You too are a page in the album of cosmic history, a late arrival in a tale that began long before you and will continue long after. As we follow the trail of clues, our journey now turns to how these layers of time connect with the motion of the galaxies themselves. The universe is not static, it is expanding. That expansion is not only written in the redshift of light, but also measured in the way galaxies drift apart. To understand this cosmic growth, we must look at Hubble's law and the comforting image of a loaf of bread rising in the oven. The idea that the universe is expanding is now so familiar that it can be easy to forget how surprising it once was. For much of human history, people assumed the cosmos was eternal and unchanging, the stars fixed forever in their places. Even when telescopes revealed countless galaxies beyond our own, many believed they floated in a static sea. But in the early 20th century, astronomers discovered that the universe is not still. It is stretching, and the galaxies are drifting apart like dancers slowly stepping back from one another. The person most often associated with this discovery is Edwin Hubble. In the 1920s, he studied the light from distant galaxies using the largest telescope of his time. By carefully analysing their glow, he noticed a pattern. The further away a galaxy was, the more its light was shifted toward the red end of the spectrum. This red shift meant the galaxy was receding, moving away from us, and the farther it was, the faster it seemed to retreat. Hubble's observation became known as Hubble's law. The speed at which a galaxy recedes is proportional to its distance. Put more softly, the universe expands evenly, like a loaf of bread rising in the oven. Imagine a ball of dough sprinkled with raisins. As the dough swells, the raisins drift apart. No raisin is the special centre. From the perspective of any single raisin, all the others appear to move away. That is how galaxies behave in an expanding universe. This bread image carries a quiet elegance. If you sit on one raisin and look outward, you will see all the others receding, and you might think you are the centre of the loaf. But if you switch to another raisin, you will see the same effect. Every raisin sees itself as the centre, not because any truly is, but because the dough itself is stretching everywhere. In the same way, Earth is not the special centre of expansion. Every observer in every galaxy would see the same pattern. Another way to picture this is with dots on the surface of a balloon. As the balloon inflates, the dots move apart. Each dot sees the others retreating, and there is no single centre on the surface itself. The expansion belongs to the balloon, not to the dots. Likewise, the expansion belongs to space, not to the galaxies. This distinction is important. Galaxies are not flying through space like ships speeding across an ocean. Instead, it is the ocean itself that is widening, carrying the ships apart. In the cosmic version, space itself is stretching, and the galaxies simply ride along with it. This is why the expansion has no preferred direction and no true centre. It is not an explosion of matter into emptiness. It is the swelling of space itself. The speed of this expansion is measured by what scientists call the Hubble constant, but instead of treating it like a rigid equation, we can soften it into a picture. For every million light-years of distance, galaxies drift away from one another by a certain speed. Today, roughly 70 kilometers per second. That means two galaxies separated by 10 million light-years would appear to move apart at 700 kilometers per second. Stretch that to 100 million light-years, and the recession is 7,000 kilometers per second. The farther the distance, the faster the retreat. These numbers are vast, but the pattern is simple. More distance equals more separation speed. It is a gentle rhythm, like ripples spreading outward on a pond. The key is that no matter where you sit in the pond, the ripples move away evenly. At first, this discovery shocked the scientific world. It meant the universe had a history. If everything is moving apart today, then in the past everything must have been closer together. Rewind far enough, and you reach a time when the universe was small, dense, and hot. A beginning. This was the seed of what we now call the Big Bang theory. The expansion discovered by Hubble was not just a curious motion. It was the echo of creation itself, still unfolding. Everyday life offers anchors to understand this otherwise daunting idea. Think of baking bread again. When you set the dough to rise, you know it began smaller. The yeast at work inside is not adding raisins, it is expanding the dough itself. Or think of a balloon at a birthday party. When inflated, the drawings on its surface spread apart. You can be sure the balloon was once smaller, even if you did not see it. In both cases, the present expansion tells you something about the past, and so it is with the cosmos. Hubble's observation showed that the universe is not a static container, but a living fabric stretching through time. The galaxies are not actors on a fixed stage. They are points painted on a canvas that is itself widening. Of course, the expansion does not affect everything equally. Here on Earth, Our bodies, our homes, and even our solar system are bound tightly together by gravity. The expansion of space is too weak to pull apart the bonds of planets, stars, and galaxies. It reveals itself only on the grandest scales, where clusters of galaxies drift apart over billions of years. Like dough rising, the effect is invisible if you look only at one raisin closely, but unmistakable if you step back and see the whole loaf. This discovery reshaped not just astronomy, but also philosophy. It told us we live in a universe with a past and a future, not a timeless void. It whispered that the cosmos is dynamic, restless, and evolving, and it prepared the stage for even deeper questions. What drives this expansion, and why does it seem to be accelerating rather than slowing down? As we drift further into this exploration, our gaze now turns to dark energy, the mysterious ingredient that pushes the universe to expand faster and faster. If Hubble's bread was rising at a steady pace, dark energy is like a hidden yeast that multiplies with time, quickening the growth. Our quiet path now carries us toward that puzzle, where the invisible emptiness itself holds the power to shape the fate of everything. When Hubble first discovered that the universe was expanding, many scientists assumed that gravity would eventually slow the process down. Galaxies attract one another, after all. Their combined pull should act like a brake, tugging gently against the outward motion. Some even thought the expansion might stop entirely one day, perhaps reversing into a great collapse. But the cosmos surprised us once again. In the late 1990s, two teams of astronomers studying distant exploding stars, called supernovae, found that galaxies were not slowing down in their drift. They were speeding up. The expansion of space itself was accelerating. It was as if the universe had pressed its foot not on the brake, but on the gas pedal. To explain this acceleration, scientists introduced the idea of dark energy. The name sounds mysterious, even ominous, but it is really a placeholder, a way of saying something unknown is causing space to stretch faster. We cannot see it directly. We cannot bottle it in a laboratory, yet its effect is written across the sky, in the way galaxies recede more quickly the further they are. An everyday way to picture dark energy is through the quiet magic of compound interest. Imagine you put money in a savings account. At first, the growth is small, but each year, the interest is calculated not only on the original deposit, but also on the interest from previous years. The total grows faster and faster, even if you never add more money. That accelerating growth is what dark energy does to space. The more the universe expands, the faster it expands, because dark energy acts like a pressure within the fabric itself. Another image is a balloon being inflated by a pump that slowly increases its pressure. At first, the balloon swells gently. Then, as the pump accelerates, the balloon's surface stretches more and more quickly. The galaxies are like dots on the balloon. They drift apart not because they are moving under their own power, but because the surface beneath them is stretching faster and faster. Dark energy makes up about 70% of the total energy content of the universe. That is, most of what exists is not stars, planets, or gas, but this invisible agent of expansion. Matter, the things we see and touch, accounts for only a small fraction by comparison. It is a startling realization. The cosmos we observe, magnificent as it seems, is only a minority portion of reality. The dominant ingredient is something we can only infer through its effects. To soften the strangeness of this, think of the wind. You cannot see the wind itself. You see leaves stirring, branches swaying, waves rising on the sea. Dark energy is like that. It does not shine, it does not glow, but its influence is written in motion. The increasing separation of galaxies, the acceleration of the cosmic fabric. There are many ideas about what dark energy could be. Some suggest it is a property of space itself, a built-in energy that has always been present, waiting to reveal its influence as the universe grew larger. Others wonder if it is something new, a dynamic field that changes over time. We do not know for certain. What we do know is that without dark energy, the universe would look very different. Its presence also changes the way we think about the future. If the expansion continues to accelerate, galaxies will drift ever farther apart. In billions of years, distant galaxies may slip beyond our event horizon, unreachable forever. The night sky, rich with stars and clusters today, may grow emptier for future observers. Our descendants may live under a quieter sky, unaware of the crowded cosmos we see now. But in the present, the acceleration gives us a chance to marvel at how finely balanced the universe is. Without dark energy, gravity might have pulled everything back into collapse. With too much of it, expansion might have torn everything apart too quickly for stars or galaxies to form. We live in a narrow window where stars shine, galaxies swirl, and life has the chance to ask these questions. To anchor this more gently, think of a campfire. Too little fuel and the flames die before the night warms. Too much fuel thrown in all at once, and the blaze roars too fiercely, consuming itself before anyone can gather. But with just the right rhythm of wood and air, the fire burns long and steady, offering both warmth and light. Dark energy may seem alien, but in its current balance, it has allowed the cosmos to unfold into a stage where we can sit by the fire of the stars. The discovery of dark energy also reshaped our understanding of emptiness. We once thought of space as a void. Now we know it not only hums with quantum fluctuations and glows with ancient light, but also holds this hidden push, this invisible driver. The silence of space is not silent at all. It is alive with influences we're still learning to name. When we look back at Hubble's law, we see it as the first whisper of this deeper story. Galaxies receding in proportion to distance were the opening notes. The acceleration discovered later was the crescendo. Together, they remind us that the universe is not a static backdrop. It is a dynamic, evolving fabric, swelling with time, carrying us along. As we follow this thread further, our path now turns to the very beginning of expansion. If today's universe is swelling faster and faster, what happened at the dawn? There, in the earliest moments, was a burst of growth far beyond anything we see now, a phase we call inflation. It was a super-fast dawn, when space itself expanded faster than light could travel, shaping everything we see today. Our quiet exploration now carries us to that strange beginning, when wrinkles in the infant cosmos were smoothed away by an expansion beyond imagination. If dark energy is the force shaping our universe's future, then inflation is the event that shaped its beginning. To step into this idea, we must imagine the universe not as the vast expanse we see today, but as a newborn, tiny, hot, and dense beyond comprehension. This was the universe less than a trillionth of a second after its birth. In that unimaginably brief instant, something extraordinary happened. Space itself ballooned outward in a sudden surge, faster than light could ever travel through it. This was the era of inflation, a super-fast dawn that set the stage for everything that followed. Now, to clarify gently, nothing was breaking the rules of relativity. Einstein's laws tell us that no object can move through space faster than light, but they place no such limit on space itself. During inflation, it was not galaxies rushing faster than light. It was the very fabric of space that stretched so quickly, carrying everything apart at a pace beyond imagination. A simple way to picture this is with a balloon. Imagine holding it between your fingers, barely inflated. Then, in a sudden breath, it swells rapidly. Dots drawn on its surface rush away from one another, not because they are moving on their own, but because the surface itself is expanding. Inflation was like that, only far more dramatic. In less than a heartbeat, the universe grew from smaller than an atom to something the size of a grapefruit, or perhaps even larger. This sudden growth solved puzzles that once troubled cosmologists. One of them is called the horizon problem. If you look at the cosmic microwave background, the faint glow left from the early universe, you find it astonishingly uniform. Every patch of sky glows at nearly the same temperature, differing by less than 1 part in 100,000. That would be easy to understand if all those regions had once been close enough to exchange heat and smooth themselves out. But in a simple Big Bang without inflation, they should have been too far apart to ever interact. Inflation explains it. By expanding so swiftly, it took regions that were once in close contact and blew them up to cosmic scales. The uniformity we see today is the memory of that early connectedness. Another puzzle inflation solves is the flatness problem. Observations tell us that the universe is very close to geometrically flat. That means if you draw a huge triangle using beams of light across billions of light years, its angles add up to about 180 degrees, just as they would on a flat sheet of paper. Without inflation, keeping the universe so perfectly balanced would be like balancing a pencil on its point. Possible for a moment, but impossible to sustain for billions of years. Inflation stretches the fabric so widely that any curvature becomes negligible, just as the surface of Earth feels flat when you stand on it, even though it is round. Inflation also gave birth to the seeds of structure. Quantum fluctuations, the tiny jitters of energy that exist even in emptiness, were stretched during this sudden expansion. Ripples smaller than an atom were pulled across the cosmos, becoming the faint imprints we now see in the cosmic microwave background. These ripples in turn grew into the galaxies, clusters and filaments that shape the large-scale structure of the universe. In other words, the stars above your head tonight trace their origins back to the restless hum of quantum energy, magnified by inflation into patterns written across the heavens. It is breathtaking to think that something so grand could emerge from something so small. Imagine a still pond disturbed by a pebble. The ripples spread outward, soft at first, then touching the whole surface. Inflation took the tiniest quantum ripples and stretched them until they mapped the entire cosmos. The universe we inhabit is, in a sense, a magnified reflection of those microscopic beginnings. Of course, inflation is still a theory. It fits the observations we see: the uniform microwave glow, the flatness of space, the distribution of galaxies, but the precise details remain uncertain. We do not yet know what field or mechanism drove the expansion. Some call it the inflaton field, a name that stands in until we understand more. Others suggest it could be linked to ideas from particle physics or string theory. For now, inflation remains both a compelling story and an open question. But whether or not we know the driver, the effect is clear. Inflation gave the universe its smoothness, its flatness, and the seeds of its structure. Without it, the cosmos might look chaotic and uneven, perhaps even unrecognizable compared to the graceful web we see today. To bring the idea back to everyday experience, think of smoothing a wrinkled sheet. If you pull it gently at the corners, some creases remain, but if you stretch it suddenly and strongly, the wrinkles vanish, leaving a smooth surface. Inflation did that to space-time. It pulled the wrinkles of the newborn universe taut, creating the even backdrop upon which galaxies could later form. There is even a poetic symmetry here. At the dawn of time, the universe raced outward faster than light, smoothing itself into a canvas. Today, billions of years later, dark energy is causing space to accelerate again, though at a much gentler pace. The story of the cosmos is one of expansion at both ends, a furious sprint at the beginning, and a quiet, steady push in its old age. As we let this image settle, the next question naturally arises. What is the shape of the fabric that inflation stretched so vast? If the universe is a canvas, is it flat like paper, curved like a sphere, or saddled like a horse's back? To answer that, we must step into the realm of geometry, where triangles and circles drawn on cosmic scales tell us whether space itself is infinite, closed, or open. Our quiet journey now turns as those shapes, where mathematics softens into pictures and the very outline of the cosmos comes gently into view. If inflation smoothed the early universe, it also left us with an intriguing question. What shape did it smooth it into? The word shape usually makes us think of familiar objects, a circle, a square, a sphere. But here we mean the geometry of the entire cosmos. On the larger scales, is space flat, curved inward, or curved outward? To answer this gently, imagine drawing triangles. On a sheet of paper, the angles of a triangle always add up to 180 degrees. That is the rule of flat space. Now imagine drawing a triangle on the surface of a ball. Because the surface curves inward, the angles add up to more than 180 degrees. Walk from the North Pole to the equator, turn 90 degrees, walk along the equator, turn 90 again, and head back to the pole. You have drawn a triangle with 3 right angles, totaling 270 degrees. This is the rule of positively curved space. Finally, picture a triangle on a saddle-shaped surface. The saddle curves outward, and the angles of the triangle add up to less than 180 degrees. This is the rule of negatively curved space. So by measuring triangles written in the fabric of the cosmos, we can test whether the universe is flat, closed, or open. Of course, we cannot draw triangles billions of light years across with rulers, but the cosmos provides its own geometry test, the cosmic microwave background, that faint glow from when the universe was just 380,000 years old. By studying patterns in this glow, tiny ripples in its temperature, we can measure how space bends. If the hot and cold spots in the background appear larger than expected, space curves inward. If they appear smaller, space curves outward. If they appear just right, space is flat. So far, the evidence points strongly toward flatness. The Planck spacecraft, launched by the European Space Agency, measured the cosmic microwave background with exquisite precision. Its results, and those of earlier missions like WMAP, tell us that the angles of our cosmic triangles add up almost exactly to 180 degrees. Space, at least across the observable universe, appears flat to within a tiny margin of error. But what does flat mean here? It does not mean space has edges like a sheet of paper. It means that, when we zoom out to the largest scales we can observe, parallel lines stay parallel, and geometry follows the rules of Euclid. You could, in theory, walk in a straight line forever without ever circling back. Still, we must tread carefully. Flat on observable scales does not necessarily mean infinite. The surface of Earth feels flat when you walk across a field, but it is really curved, too vast for you to notice without circumnavigation. The universe may be similar. It may be flat within our cosmic horizon, but curved gently on scales we cannot yet see. Or it may truly stretch without limit, extending forever into regions beyond our reach. The idea of infinity is dizzying. How can something have no end? How can it go on without boundary? Here, it helps to soften the concept with images. Think of standing at the shore of the ocean. The horizon stretches endlessly. You know, in principle, the ocean is finite, yet from where you stand it feels infinite. Or imagine staring into a mirror angled toward another mirror, reflections repeating into the distance. You cannot see the end of the repetition, even though the mirrors themselves are bounded. Infinity in space may be like that. Perhaps real, perhaps an illusion of perspective, but either way it invites us to wonder. There is another gentle way to approach this. Imagine a vast quilt stitched by many hands. Each square is a galaxy cluster, each thread the filaments of cosmic matter binding them together. From your place on the quilt you see only a patch, but the quilt may stretch further than you can see, perhaps endlessly. Whether it ends or not, the stitching continues beyond your sight. Flatness also raises questions about destiny. A positively curved universe, like a sphere, might eventually collapse under its own gravity. A negatively curved universe might expand forever. A flat one rests delicately between. With dark energy driving acceleration, the flat universe seems poised for eternal expansion, carrying galaxies further apart until the night sky grows empty. But destiny aside, the present fact is this: on the grandest scales we can measure, space is astonishingly flat. The cosmic microwave background acts as our giant triangle, our geometry lesson written in light from the infant universe. It reassures us that the early burst of inflation did its job, stretching wrinkles smooth and balancing the cosmos like a carefully laid sheet. Of course, the human mind craves certainty. We want to know definitively, is it infinite or merely very large? But science, for now, leaves us with humility. We can measure only so far. Beyond the horizon, the answer remains hidden. Flatness is our best clue, but not our final proof. And perhaps that is fitting. The shape of the universe is not a puzzle to be solved once and for all, but a reminder of our place in it. We stand in the middle of an enormous canvas, tracing triangles with starlight, inferring geometry from ancient glow. Whether the canvas is endless or merely vast, the act of wondering binds us to it. As we drift further along this path, our next step brings us to an even subtler thought. What if space is finite yet still has no edge? Could it loop back on itself like the surface of Earth, allowing a traveller to journey forever without finding a wall? Our quiet exploration now turns to this idea of finite but unbounded space, where donuts, spheres, and other strange shapes become metaphors for the fabric of the cosmos. When we imagine space, it is tempting to think of it as either infinite or cut off by a wall. But nature often offers a third option, something subtler and more elegant. The universe could be finite and yet have no boundary at all. To many ears, this sounds contradictory. How can something be limited but without edges? To soften the paradox, let's take a quiet walk around Earth. If you start at one point on Earth's surface and keep walking in a straight line, eventually you will return to your starting point. You will never encounter a cliff at the end of the planet. The surface is finite but unbounded. It has no edge you can fall off. Its finiteness is expressed not by walls but by curvature. In the same way, space could loop back on itself. A traveller moving forever in one direction might eventually arrive back where they began, without ever finding a border. This idea is often called a closed universe, shaped like a higher dimensional sphere. It is difficult to picture directly, but we can rely on analogies. Just as the two-dimensional surface of a ball curves into a shape that is finite but edgeless, our three-dimensional space could curve into a higher dimensional form, finite but smooth. We cannot step outside to see the curvature, but we can infer it by studying how light travels and how geometry behaves within it. Another possibility is that space is shaped more exotically. Instead of a sphere, it might have the geometry of a torus, a shape like a donut. Imagine playing a video game where walking off the right side of the screen makes you reappear on the left. That is how a torus behaves. In such a universe, if you travelled far enough in a straight line, you might reappear where you started, but along a different route than you would in a spherical cosmos. The topology, the deep structure of how space is connected, can be surprisingly rich. These ideas may sound abstract, but they can be softened with everyday anchors. Consider the old arcade game Pac-Man. In its maze, moving off the edge of the screen does not mean you vanish. You simply reappear on the opposite side. The game world is finite in extent, but has no impassable edge. It is a playful metaphor for a cosmos that may be similarly wrapped around itself. Scientists search for signs of such topology in the sky. If the universe were closed in this way, light might circle around and reach us more than once, producing repeating patterns in the cosmic microwave background. Imagine standing in a hall of mirrors. You see the same image reflected again and again. Astronomers look for those reflections in the ancient light of the universe. So far, the evidence points to no obvious repetitions, but the possibility remains, hiding at scales just beyond our observable horizon. A finite yet unbounded universe would also change how we think about travel. Imagine building an impossibly fast ship and setting off in one direction forever. In an infinite universe, you would always find new regions, never looping back. In a finite closed universe, you would eventually return home, not by turning around, but by continuing straight. It is a journey both endless and circular, a cosmic marathon where the track folds back on itself. This notion, that space could be finite without edges, eases the discomfort many feel when they hear the word infinity. Infinity is hard to grasp. It stretches beyond imagination. Always more, always further. But finiteness without borders is something our intuition can touch. We know what it means to walk around Earth. We know what it means to move through a looped world like Pac-Man. These metaphors let us rest gently with the idea, even if the reality exists in dimensions beyond our senses, and yet humility is needed. The data we have so far suggests the universe is very close to flat. That could mean it is infinite. It could also mean it is finite, but so large that its curvature is too subtle for us to detect. From our tiny perch, the quilt of space looks flat, but its stitching may bend beyond the horizon. There is a quiet beauty in this uncertainty. The cosmos does not hand us clear answers. It invites us into possibilities, each one strange and wonderful. Whether infinite or finite without edges, space asks us to widen our imagination, to accept shapes that defy everyday experience. To soften this with another anchor, think of music. A song can loop endlessly, repeating verses without ever feeling cut off, or it can build to a finale, finite but smooth, no harsh ending. Either way, the experience is continuous. Space may be like that, a melody either infinite in repetition or finite in graceful closure, but never cut short by a jarring stop. As we let these possibilities settle, we find ourselves returning to an earlier image, the balloon. Inflation stretched it, Hubble's law expands it, and dark energy accelerates it. But the balloon is not just a picture of expansion, it is also a picture of curvature. Its surface has no edges. Its finiteness is hidden in its looping geometry. Our quiet exploration now turns to this balloon analogy more deeply, where ants crawling on its surface reveal the secrets of how space itself can grow without ever needing a center or a wall. We have already visited the balloon as a picture for cosmic expansion, but it is worth slowing down and stretching that image further, because within it lies one of the most helpful ways to imagine space itself. Take a balloon from a birthday party and draw a few tiny dots on its surface. Each dot is a galaxy. When the balloon is small, the dots are close together. As you blow air into it, the surface expands and every dot drifts away from the others. None of the dots is moving on its own. They are not crawling across the surface. The surface itself is stretching, carrying them apart. This is what cosmologists mean when they say the universe is expanding. Galaxies are not flying through space like ships sailing away from a harbour. The very fabric of space between them is swelling like the latex of the balloon. Now notice something subtle. There is no special centre on the surface of the balloon. If you are one of the drawn dots, every other dot appears to be receding from you. From your perspective, you might think you are the centre of expansion. But if you switch your view to another dot, the same is true. Every point sees itself as the middle of the balloon story. This is exactly what astronomers find. From Earth, it looks like all galaxies are rushing away from us, as though we are the centre of the universe. But if you lived in another galaxy, you would see the same pattern. Expansion has no preferred location. It is everywhere at once. The balloon also softens another misconception. People sometimes imagine the Big Bang as an explosion, matter flinging outward into empty space. But in the balloon picture, there is no outside surface that the dots are flying into. The only surface that exists is the one that expands. Similarly, the universe is not expanding into pre-existing emptiness. Space itself is growing. The expansion is not a motion through something, it is the stretching of the something itself. Of course, the balloon is only an analogy. The true universe is not the two-dimensional skin of a sphere, but three-dimensional space. The balloon's surface is curved into a higher dimension we cannot perceive directly. We are like ants living on the balloon's surface, able to crawl along it but unable to see the third dimension that gives it shape. In the same way, we inhabit three-dimensional space without access to whatever higher dimensional shape it might rest in. Even so, the analogy teaches us something important about edges. On the balloon's surface, there are none. An ant could crawl forever without finding a cliff or a wall. The surface is finite but unbounded. If the universe is like that, it could also be finite in volume, yet without borders. This softens the fear of falling off the edge of space. There may be no such edge to find. The balloon picture also illustrates how expansion works on different scales. If you look closely at the balloon while it inflates, the dots themselves do not stretch. Only the surface between them grows. Likewise, galaxies do not expand. Stars and planets do not swell with the universe. Gravity holds them together. It is only the vast regions between clusters of galaxies, the cosmic fabric itself, that expands. This is why your body, your home, and even your galaxy remain stable while galaxies as a whole drift apart on the larger scales. To anchor this more gently, think of raisins in bread dough once again. As the dough rises, the raisins spread apart, but they themselves do not grow. Their skins remain taut, their seeds remain bound. The expansion belongs to the dough, not to the raisins. The balloon also helps us imagine the future. If dark energy continues to accelerate the expansion, then the balloon of the cosmos will keep swelling faster and faster. Distant galaxies will slip further away, and the night sky will eventually grow emptier. Future civilizations, billions of years from now, may find themselves on a balloon so stretched that most of the other dots are invisible. They may see only their own galaxy and perhaps a few neighbours, never knowing the rich web of galaxies we can see today. And yet, there is something tender in this thought. It reminds us that our moment is precious. Right now, the balloon is still crowded with dots. We can still glimpse the wider pattern of the universe, still receive light from galaxies billions of years old. We are reading the cosmic story at a time when most of its pages are still visible. The balloon also encourages humility. Just as an ant on the surface cannot easily tell the shape of the balloon in higher space, we cannot yet know the ultimate topology of our universe. It may curve back on itself like a sphere, or wrap in loops like a torus, or extend flat without limit. From our small perch, we can only study the clues written in the light we see, but even in its limits the analogy comforts. It whispers that expansion need not mean chaos. It is not galaxies rushing frantically outward. It is the quiet stretching of a fabric, smooth and even, carrying all things gently apart. And perhaps the most important lesson is this: the balloon's surface has no centre on the surface itself. The centre exists only in the higher dimension, in the air filling it. For the universe, there may be no true centre at all. Every place is as central as every other. This idea, called the cosmological principle, assures us that the universe looks broadly the same in all directions, no matter where you stand. It is a principle of equality, reminding us that our corner of the cosmos is not privileged, but part of the whole. As we let this image drift in our minds, the story of the universe opens into its earliest visible memory, the cosmic microwave background. If the balloon is the surface, then the glow of that background is the paint upon it, the faint colour left from when the universe was still a newborn. Our path now carries us into that light, where the afterglow of creation itself tells us about the shape, age and contents of everything we see today. When you sit by a campfire at night, the flames eventually fade. The logs crumble into embers, and the embers into faint wisps of heat. Even long after the fire has burned down, the warmth lingers, soft and steady. The universe carries something very much like that, a faint glow from its own early fire, the cosmic microwave background. It is not dramatic like the Milky Way arching across the night sky. It is not visible to your eyes at all, yet it fills the heavens in every direction, a quiet afterglow from the moment when the universe was very young. To find where this glow began, we must travel back to when the universe was just 380,000 years old. That sounds like a large number, but against the age of the cosmos, 13.8 billion years, it is an infant's cry. At that time, the universe was still hot, dense, and glowing with light, but it was also filled with a thick fog of charged particles. Photons, the tiny packets of light, could not travel far before colliding with electrons. The cosmos was like a room filled with smoke. Light bounced around endlessly, unable to escape. Then came the moment scientists call recombination. The universe cooled enough for electrons to settle down and bind with protons, forming neutral atoms of hydrogen. The fog lifted. For the first time, light was free to travel. Those photons began their journey then, streaming across space. They have been travelling ever since, stretched by the expansion of the universe, softened from brilliant visible light into faint microwaves. Today, they form a background glow at a temperature of about 2.7 degrees above absolute zero, the coldest possible temperature. You might wonder, if this glow surrounds us, why can't we see it? The answer is that our eyes are tuned to visible light, reds, blues, and greens. The cosmic microwave background has shifted into wavelengths far longer than the eye can detect. But with special instruments, radio dishes, space satellites, we can tune into this whisper. And when we do, we find the entire sky glowing faintly and evenly. No patch is brighter than another, at least not by much. The discovery of this glow came almost by accident. In the 1960s, two engineers, Arno Penzias and Robert Wilson, were testing a radio antenna for satellite communication. No matter what they tried, they picked up a persistent hiss of static, like the hum on a badly tuned radio. They cleaned the antenna, chased away pigeons roosting inside it, and checked their equipment, but the noise remained. Eventually they realised it was not equipment at all. It was the sky itself, humming softly. They had stumbled on the afterglow of the Big Bang. For this, they later received the Nobel Prize. Since then, astronomers have studied the cosmic microwave background with increasing precision. Satellites like COBE, DEWMAP, and Planck have mapped it in detail, painting a picture of the universe as a baby. Imagine the embers of a fire photographed with an ultra-sensitive camera, not just glowing evenly, but shimmering with the tiniest flickers of hot and cold. The cosmic microwave background is like that. It is nearly uniform, but not perfectly so. There are tiny variations, just one part in 100,000, small patches slightly warmer or cooler than others. Those tiny ripples are among the most important discoveries in cosmology. They are the seeds from which all structure grew. Where the glow was a little denser, gravity slowly gathered matter into clumps. Those clumps became galaxies, stars, planets, and eventually people. Every spiral of the Milky Way, every cluster of galaxies traces its ancestry back to those faint mottled patches in the background glow. Think of flour stirred into bread dough. If the flour is perfectly smooth, the bread rises evenly, bland and uniform. But if there are little lumps, those lumps set the texture of the loaf. The universe works the same way. The tiny lumps in the background glow gave texture to the cosmos, guiding how matter gathered into webs and walls. Without them, we might live in a universe with only thin gas, no stars, no planets, no life. The cosmic microwave background also acts as a cosmic ruler. By studying the size and distribution of those ripples, scientists can learn the shape of space. If the universe were curved inward, like a sphere, the patterns would appear larger than expected. If it were curved outward, like a saddle, the patterns would appear smaller. As it is, they appear just the right size, telling us that the universe is remarkably flat on the scales we can observe. And the glow does more than tell us about shape. It tells us about contents. By analysing its spectrum, the spread of energy across different wavelengths, we can learn what the universe was made of in its infancy. The results show that only about 5% of the cosmos is ordinary matter, the kind that makes up stars, planets, and people. About a quarter is dark matter, invisible but heavy. And the majority, as we've already met, is dark energy, the strange driver of expansion. So in this faint microwave glow, we hear the echoes of three truths at once: the geometry of space, the ingredients of the cosmos, and the seeds of structure that became galaxies. It is as though the baby photo of the universe carries, in its pixels, the outlines of everything to come. There is something profoundly comforting in this. The light around you right now, the glow of your lamp, the shimmer of the stars overhead, carries with it the same essence as that background. Photons are ancient travellers, many of them older than Earth itself. The room you sit in is gently bathed in light that began its journey nearly 14 billion years ago. You cannot feel it, but it is there, like the warmth of embers lingering long after the fire has gone. As we drift further into this story, we see that the cosmic microwave background is not perfectly smooth. Its tiny variations are the first fingerprints of creation. By studying those patterns closely, we can read the blueprint of the cosmos, learning how galaxies and clusters emerge from almost nothing. Our quiet exploration now turns to those patterns in the glow, where the speckles of ancient light became the scaffolding for everything we know. When astronomers first mapped the cosmic microwave background, they were astonished not only by its evenness, but also by its tiny imperfections. Across the sky, the glow is almost uniform, like a softly painted wall. Yet when you look closer, with instruments sensitive enough to notice differences as small as 1 part in 100,000, you find speckles, little regions ever so slightly warmer or cooler than others. These are the fingerprints of the young universe, written in light. At first glance, such tiny variations might seem unimportant. A fraction of a degree here, a fraction there, barely noticeable against the background of 2.7 degrees above absolute zero. But these small ripples are everything. They are the seeds from which galaxies grew, the scaffolding upon which cosmic history was built. To bring this into everyday terms, imagine mixing flour into bread dough. If the flour is perfectly smooth, the dough rises into a plain uniform loaf. But if there are small lumps or slight variations, the loaf takes on texture and character. The universe is like that. Without those tiny lumps in the microwave background, matter would never have gathered into stars or planets. The cosmos would have remained a featureless fog. With them, gravity had a blueprint. Over billions of years, it pulled matter into clumps, shaping the spirals of galaxies and the webs of clusters we see today. These patterns are not random. They follow the quiet music of physics. In the infant universe, sound waves rippled through the hot plasma of particles and light. Yes, sound waves, though not sound in the way your ears would hear it. These were compressions and rarefactions in the cosmic fluid, oscillations of pressure and density. When the fog cleared at the time of recombination, those ripples froze into the light itself, leaving imprints in the microwave background. Scientists study these ripples through a tool called the power spectrum. Instead of plotting every dot of hot and cold on the sky, they measure how large the ripples are on average. How many are big, how many are medium, how many are small. The result is like the fingerprint of a song, the distribution of its notes across frequencies. The microwave background has its own song written in ripples of light, and by reading it, we can learn the universe's properties. From these patterns, we know that the cosmos is remarkably flat on large scales. If the universe were curved inward like a sphere, the ripples would look larger. If it were curved outward like a saddle, the ripples would look smaller. Instead, they appeared just right, pointing to a flat geometry within our horizon. This confirms what inflation predicted and what earlier hints suggested. Our cosmic stage is balanced delicately, stretched smooth like a sheet, pulled taut. The ripples also reveal the contents of the universe. By comparing the heights of different peaks in the power spectrum, the loudness of different notes in the cosmic song, astronomers can deduce how much matter, and dark energy are present. The results are striking. Only about 5% of the cosmos is ordinary matter, the atoms that make up stars, planets, and people. Roughly 25% is dark matter, unseen but heavy, binding galaxies with its gravity. The rest, nearly 70%, is dark energy, the mysterious force driving expansion. All of this is encoded in the speckles of a faint glow that seems at first to say nothing at all. Think of it like looking at the rings of a tree. At first they seem just circles, but if you know how to read them, they tell you the story of rainfall, drought, fires, and growth across centuries. The microwave background is like those rings. To a casual glance, it is nearly uniform. To a trained eye, it is a record of the entire cosmos, written when it was still a baby. There is poetry in the fact that the most delicate variations in temperature, fractions of a degree above the coldest possible, hold the key to everything we know. Out of those speckles came the stars that light our skies, the galaxies that sweep in grand spirals, the planets that cradle oceans, and the living beings who now reflect on it all. In a way, you could say we are the descendants of tiny ripples in ancient light. The patterns also remind us of humility. They tell us how much we can know, but also how much remains hidden. We can measure the seeds of galaxies, but not yet the full story of dark energy. We can trace the geometry of space, but not yet its ultimate fate. The background glow gives us a map, but some lands are still beyond its borders. Still, what a gift it is. With satellites like COBE, WMAP, and Planck, we have transformed a faint radio hiss into a cosmic photograph, a detailed map of the universe's first visible moment. We can hold that map alongside the galaxies we see today and connect the dots, tracing the growth of structure across nearly 14 billion years. To soften the strangeness of all this, return to the campfire. Imagine you walk away from the fire long after the flames have faded. In the air, faint warmth lingers, carrying the memory of heat. If you had instruments sensitive enough, you could trace tiny currents of warmth where the fire's embers had burned hottest. The cosmic microwave background is just that. Lingering warmth, patterned by ancient ripples, still carrying the story of how the cosmos was lit. As we follow the thread of this story, our path now carries us beyond observation into speculation. The cosmic microwave background marks the farthest we can directly see. But what lies beyond that horizon? Does the universe have boundaries? Or is it part of something larger still? Our quiet exploration turns now to the edges of imagination, where branes, bubbles, and holograms invite us to wonder whether space itself has limits, or whether those limits belong only to our sight. We've now walked as far as light itself will carry us to the cosmic microwave background, the first visible moment in time. It is tempting to stop there and imagine it as a wall, the farthest edge of the universe, the end of space itself. But that is a misunderstanding. The background is not a wall, it is more like a veil. It marks the limit of what we can see, not necessarily the limit of what exists. The question of whether the universe has a true boundary is one of the oldest in human imagination. Our ancestors pictured crystal spheres surrounding the stars, or domes arching overhead. Even now it is easy to slip into thinking of space as a giant room with walls. But when scientists speak of space, they mean something softer, Space is not a container holding galaxies like marbles in a box. It is the fabric itself, woven of distances, times, and energies. Asking for its edge is a little like asking for the edge of a melody. A song can end, but it does not have a wall. Still, there are models in modern cosmology that flirt with the idea of edges, not as walls you can bump into, but as connections to other realms. One such idea comes from brane cosmology, inspired by string theory. In this picture, our universe might be a three-dimensional membrane, what physicists call a brane, floating in a higher dimensional space. Imagine a thin soap film stretched across a wire loop. The film itself is two-dimensional, smooth and flexible, but it floats in a three-dimensional room. Creatures confined to the soap film would never know the larger room existed, unless some ripple disturbed their world. Our universe could be like that soap film, a flexible sheet embedded in a larger bulk of dimensions we cannot perceive. The galaxies, stars, and atoms we know would all be confined to the sheet. If that is true, the edge of our universe is not a physical cliff, but a higher dimensional separation, like the place where the soap film meets the air around it. We, the ants crawling on the film, would never see beyond it. Another analogy is the surface of a trampoline. Stand on it, and you can move north, south, east, or west across the fabric. The trampoline has edges if you step off, but if you were confined only to the fabric, those edges would be inaccessible. To you, the fabric would be everything. If our cosmos is like that, then edges may exist in a higher dimensional sense, but not in the one we experience. This idea does more than satisfy curiosity. It may connect to deeper mysteries like dark energy. Some versions of brane cosmology suggest that the accelerated expansion of our universe could be influenced by interactions with higher dimensions. Perhaps space itself is being tugged, stretched, or influenced by something just beyond our sight, like a ripple passing through the soap film. We should pause here though. These ideas are beautiful, but they remain speculative. They are not confirmed by observation. Science holds them gently as possibilities, waiting for evidence that may or may not come. For now, the most reliable story remains the one we can measure: horizons, expansion, the microwave glow. But part of the wonder of cosmology is that it allows us to imagine, to test, to dream about possibilities beyond the data. When we think of edges this way, we discover they are not abrupt ends, but invitations. They invite us to consider what lies beyond horizons, beyond dimensions, beyond what our senses can tell us. They invite us to step into metaphor. Just as sailors once wondered what lay past the ocean's horizon, we now wonder what lies past the cosmic horizon. The sailors eventually discovered new continents. We may discover new dimensions, or we may simply learn that our map of the known expands further than we imagined. To bring this back to everyday life, think of standing before a foggy window. On the near side, you see your own reflection. On the far side, shapes move faintly but cannot be resolved. The window is not a wall, it is a veil. In the same way, the cosmic microwave background is not a hard stop. It is a veil that hides earlier moments from us, and perhaps realities beyond. This is also why cosmologists are careful with language. They rarely say the universe ends, they say we have an observable limit. Beyond that limit, space may continue indefinitely, or it may loop back on itself, or it may be part of a greater fabric in higher dimensions. Each option is extraordinary, none requires a wall, so when you hear the phrase edge of the universe, it is better to picture not a cliff but a shoreline. From the beach, you see the horizon stretch across the water. You know the ocean continues, but your eyes cannot reach further. The cosmos is like that. The edge we speak of is the edge of our sight, not the edge of existence. As we let this idea settle, another question rises naturally. If our universe could be a soap film in higher space, could there be other films floating nearby? If inflation produced more than one region of space, each might be its own bubble, drifting in a cosmic foam. Our quiet path now turns to this vision of bubbles and domains, where universes touch like soap bubbles in a sink, each one with its own story, each one hinting at a multiverse beyond our own. If our universe can be pictured as a balloon or a soap film, then it is natural to wonder, might there be more than one? Could space itself be part of a larger foam, a collection of bubbles drifting side by side? This idea arises from the theory of eternal inflation, and though it belongs to the speculative edges of cosmology, it carries a beauty that makes it worth exploring. Inflation, as we discussed earlier, was the burst of expansion that smoothed the newborn universe. But some versions of the theory suggest that inflation did not end everywhere at once. Instead, it may continue eternally in some regions while ending in others. Where it ends, a bubble forms, a region like our own, where galaxies, stars and planets can develop. Where it continues, space keeps swelling, generating more and more bubbles. The result is a cosmic foam, countless bubble universes, each sealed off from the others by expanding space. Imagine blowing soap bubbles in a sink. Each bubble has its own surface, its own shimmering interior, its own story of shapes and colours. Some touch gently at their edges, some drift apart. To an ant living on the surface of one bubble, the others would be invisible, forever out of reach. In this picture, our universe is just one bubble among many. These bubble universes could be similar to ours, or they could be very different. The laws of physics inside each bubble might not match. In one, stars and galaxies might form as we know them. In another, the constants of nature might be tuned differently, preventing atoms from forming at all. In yet another, there might be no light, no matter, only strange fields of energy. The multiverse, if it exists, could contain infinite variety. Eternal inflation also suggests that new bubbles are always being born. While we live inside one that has long since cooled and formed galaxies, the space beyond continues to inflate, spawning new domains. In this sense, creation never stops. It is not a single event in the past, but an ongoing process, forever generating new universes in the vast sea of space. This picture can feel overwhelming, so let's anchor it with something gentler. Think of yeast in bread dough. As the dough rises, bubbles form throughout. Some bubbles grow large, some remain small, some merge with neighbours, some collapse. Each bubble is its own little world, separated from the others by thin walls of dough. The multiverse imagined by inflation is like that. We live inside one of the bubbles. We cannot touch the others, but we can imagine them swelling alongside ours. There is also the idea of domain walls, which arise in certain theories of particle physics. In these models, space can settle into different states, like a field of grass bending in one direction here, another direction there. The boundaries where these regions meet are called domains, and the walls between them are boundaries of energy. In the early universe, such domains may have formed and disappeared, leaving imprints on the cosmos. Some speculate that entire universes could be separated by such boundaries, each domain with its own physical rules. To soften this further, picture a quilt made of many patches, each with its own colour and pattern. From one patch to the next, the stitching marks a boundary. Yet the quilt as a whole is continuous. A multiverse separated by domains would be like that quilt, each patch a universe, each seam a border we cannot cross. Now, one might ask, is there any evidence for these bubbles or domains? The honest answer is no, not yet. They remain in the realm of speculation, ideas inspired by theories of inflation and high-energy physics. Some scientists have wondered if bubbles colliding might leave faint signatures in the cosmic microwave background, like rings or bruises in the glow. So far, no clear evidence has been found. The cosmic foam remains a possibility, not a proven fact. But even as speculation, the idea offers perspective. It reminds us that our universe, as vast as it is, may not be the whole story. It may be a single chapter in an infinite library, a single bubble in a froth of countless worlds. And if that is so, then our question, does space end, takes on another layer. For our bubble, there may be no edge within, but beyond there may be other bubbles, forever hidden, yet real in their own right. This does not diminish our place. It enriches it. Think of a single seashell on a beach. Its pattern is unique, its ridges shaped by the waves. To hold it is to hold a world in miniature, yet it is one among countless shells scattered on the sand. Our universe may be a single shell, exquisite and complete, but joined in spirit with others in the great tide of existence. And so, when you look up at the night sky, remember, the stars you see belong to our bubble. Their light is confined here, their history written on our fabric of space. But beyond what we can ever see, other bubbles may shine with their own light or remain forever dark, separate but parallel. The possibility itself is enough to stir wonder, even if no telescope will ever catch their glow. From here, the story leads us gently toward other exotic models, ideas even stranger than bubbles and domains. Some speak of rotating universes where time loops back on itself. Others imagine our three-dimensional reality as a projection from a distant surface. Our quiet exploration now turns to these visions, speculative yet poetic, where the edges of physics blend with the edges of imagination. So far, our exploration has carried us through familiar landscapes of science: horizons, expansion, background light. Then we drifted into speculation about bubbles and domains. But at the farthest edge of theory lie ideas even stranger, concepts that bend not only our understanding of space, but also our intuition about time and reality itself. These exotic models are rarely treated as final truths. Instead, they are thought experiments, lanterns that light possible paths, even if we never walk them. One such idea comes from the mathematician Kurt Gödel, famous for his incompleteness theorems in logic, but also for proposing an unusual model of the universe in 1949. Gödel imagined a cosmos that does not just expand or sit still, but rotates. In this rotating universe, the fabric of space-time itself would swirl like water in a great whirlpool. And here's the strange part. In such a geometry, time loops would be possible. A traveller could, in theory, set out on a journey and return not only to the same place, but also to the same moment, reliving their own past. This notion, while mathematically consistent with Einstein's equations, seems not to describe the real universe we observe. We see no evidence of global rotation on such a scale. Still, Gödel's rotating universe is a reminder that the laws of relativity allow more possibilities than our everyday intuition suggests. The cosmos could, in principle, have been built in ways far stranger than what we see. Another exotic idea is the holographic principle. At first glance, it sounds like science fiction, a suggestion that everything we experience, every star, every planet, even you and me, might be encoded on a distant surface, like a three-dimensional hologram projected from a two-dimensional film. The principle grew from attempts to understand black holes. When matter falls into a black hole, it seems to vanish. But physicists realize that the information about that matter is not lost. It is encoded on the surface of the black hole, its event horizon. This led to the daring thought, what if the entire universe works this way? If true, it would mean that our three-dimensional reality is like the moving picture cast by a flat screen far away. The surface would carry the information, and what we call space would be the unfolding projection of that information. Everyday anchors can help soften the strangeness. Think of a snow globe. Its surface holds all the detail, the glitter, the painted houses, the swirling patterns. Inside, the scene feels three-dimensional, but its essence is captured on the thin glass shell. Or think of a book. The story lives in your imagination in 3 dimensions, but its instructions are encoded in ink on a flat page. The holographic principle is not proven, but it has surprising mathematical support. It suggests that the universe's deepest laws may be simpler when described on a boundary, rather than in the space we inhabit. If the cosmos is like a song, perhaps the melody is written on the edge, while we live inside the sound it creates. These exotic models invite us to rethink what we mean by edges and boundaries. In Gödel's rotating universe, the boundary of time itself could fold back on itself, making before and after blurry. In the holographic principle, the boundary might not be a wall at all, but a canvas on which everything is written. Neither picture changes the fact that we live here, now in the unfolding cosmos, but they remind us that our intuitive categories, inside versus outside, past versus future, may be softer than we think. Even if these models never describe our universe exactly, they are valuable. They stretch the imagination. They test the limits of Einstein's equations and quantum theory. They show us that physics is not only about observation but also about possibility. Sometimes, by wandering down strange roads, scientists find clues that help explain the world we do see. To anchor this in daily life, think of walking through an unfamiliar forest. Some paths are dead ends, leading nowhere. But even a dead end teaches you about the lay of the land. You learn where the rocks are, where the river bends, where the soil grows soft. Exotic models in cosmology are like those exploratory trails. They may not lead to the final clearing, but they shape our map of what might be. They also remind us of the poetry of science. Imagine a universe that loops time like a song on repeat. Imagine a universe that encodes itself on a distant surface, like a movie projected in a theatre. Even if these images are not literal, they invite us to look at reality with fresh eyes. And sometimes that fresh perspective leads to discoveries in less exotic corners. Of course, one might ask, does this mean our universe could truly be a hologram? Could we in some sense be shadows on a distant wall? The honest answer is that we do not know. For now, the holographic principle remains a powerful mathematical tool, a way of simplifying complex problems. Whether it is literally true about our cosmos is an open question, but there is comfort in this uncertainty. We do not need final answers to feel awe. The very fact that such possibilities exist, allowed by our deepest equations, hinted at by black holes, dreamed of by thinkers, gives us permission to marvel. The universe is more than a set of distances and times. It is a mystery that continues to unfold, always inviting us to imagine. As we let these visions settle, the trail now carries us gently toward the multiverse question in earnest. If bubbles and domains hint at other universes, and exotic models hint at deeper structures of reality, then the next step is to ask, how many kinds of multiverse could there be? Our quiet exploration now turns to libraries of infinite books, shelves upon shelves of worlds where every variation of the cosmos might be written. Having wandered through the ideas of bubbles, domains, and exotic models, it is natural to ask, if our universe is not the only one, then what other kinds might exist? The word multiverse gathers many possibilities under one name, but in truth there are several different flavours of the idea, each born from different corners of physics and philosophy. Some are mathematical, some are quantum, and some are rooted in cosmic inflation. All are speculative, yet each opens the door to wonder. The first type is the one we already touched on, the inflationary multiverse. In this picture, inflation is not a one-time event, but an eternal process. Regions of space continue inflating, spawning new bubble universes endlessly. Our cosmos is just one bubble among many, floating in a sea of others. Some bubbles may be similar, with galaxies and stars like ours. Others may be strange beyond imagining, with laws of physics tuned so differently that no familiar structures form, If this is true, then the multiverse is like a foam, each bubble a separate world, unreachable and hidden from the rest. A second type comes from quantum physics and the idea known as the many worlds interpretation. Quantum theory tells us that particles exist in states of possibility until measured, like a coin spinning in the air, both heads and tails at once, until it lands. In the many worlds view, every possibility is realized. When a choice occurs, the universe splits, one branch for heads, another for tails. At every moment, countless branches proliferate, creating a vast tree of realities. In one universe, you chose coffee this morning. In another, tea. In one, you caught the bus on time. In another, you missed it. The many worlds interpretation suggests that every quantum possibility plays out, not in imagination, but in parallel universes just as real as ours. The third type is more mathematical. Physicist Max Tegmark has suggested that mathematics itself is the ultimate reality. Every possible mathematical structure exists, and each one corresponds to a universe. In this mathematical multiverse, our cosmos is simply one of the many solutions to the equations of logic. Somewhere, there are universes where the geometry is entirely different, where time flows in loops instead of lines, or where dimensions stack in ways we cannot picture. In this view, existence is as broad as mathematics itself, an infinite library of structures, each one real in its own domain. Another idea arises from the anthropic principle, which observes that the constants of our universe, the strength of gravity, the charge of the electron, the speed of light, seem finely tuned for life. If they were slightly different, stars might never form, or atoms might never bond. Why do they take just the right values here? The multiverse offers one answer. Perhaps they vary across different universes. We live in one where the constants allow life, because only in such a universe could beings like us arise to ask the question. It is like finding yourself in a house with breathable air. You're surprised at the fit, but you could not exist in a house without it. To soften the variety of multiverse types, imagine a vast library. On its shelves sit books of every kind. Some books tell stories very much like ours, with only minor variations, a word changed here, a sentence there. Others are wildly different, written in unfamiliar scripts, their plots unrecognizable. Some are slim pamphlets, universes short-lived. Others are endless tomes, universes vast and complex. The inflationary multiverse is like one section of this library, where each book is a bubble universe. The many worlds interpretation is like a branching story, where every decision in the plot creates a new volume. The mathematical multiverse is the library itself, containing not only the books we can imagine, but also those written in languages no one has ever seen. The beauty of the multiverse idea is that it expands our sense of possibility. Our universe, as immense as it is, becomes one among countless others. It humbles us, reminding us that what we call everything may be only a fraction of a greater whole. But it also comforts us, suggesting that even if our story is finite, the library of existence is endless. Of course, there are challenges. How can we test these ideas? If other universes are forever beyond our reach, do they belong to science or only to imagination? That question leads us gently to the next session. But before we step there, it is worth pausing to appreciate the richness of the picture. Whether or not the multiverse is real, thinking about it broadens our horizons. It shows us that physics is not just about measurements and equations, it is also about wonder, about stretching our minds beyond what we can see. And perhaps there is a poetic symmetry here. Just as sailors once suspected other lands beyond the horizon, just as readers sense other stories beyond the page, we sense that our universe may not be alone. Whether those other universes exist or not, the act of wondering connects us to the tradition of curiosity that has always defined us. As we drift further along this path, Our quiet exploration now turns to a challenge. How can we tell the difference between speculation and science? How do we test the untestable? The trail of questions leads us toward the problem of falsifiability, where maps of unreachable lands remind us of both the power and the limits of our imagination. The multiverse is an idea that sparkles with imagination, but it also stirs one of the deepest questions in science. How do we tell the difference between speculation and knowledge? Science has always prided itself on testing. A theory is not just a story. It is a story with consequences, predictions that can be measured against reality. But what happens when the predictions belong to places we can never reach? This is the challenge of the multiverse. If other universes exist, separated from us by domains of inflating space, or by the branching of quantum possibility, how can we ever test that? No telescope can look beyond our cosmic horizon. No spacecraft can cross into a parallel bubble. If evidence cannot be gathered, does the idea remain scientific, or does it slip into the realm of philosophy? To frame this gently, imagine maps of lands beyond the sea in the age of exploration. Early cartographers drew coastlines they had never seen, filling empty spaces with imagined mountains and rivers. Some of their guesses were wrong. Others hinted at real continents yet to be discovered. The maps were useful, even when they were incomplete. They guided voyages, inspired explorers, and provided starting points for later corrections. The multiverse may be like those early maps. It sketches possibilities beyond our reach, not to deceive, but to remind us that the horizon may not be the end. There are some ways, however, that science might glimpse indirect signs. For example, if our bubble universe ever collided with another in the distant past, that encounter might have left scars, circular patterns in the cosmic microwave background, subtle bruises on the sky. Astronomers have searched for such features, though so far no convincing evidence has been found. The search itself is valuable, a way of asking the question with instruments rather than just imagination. Another indirect approach comes from inflation. If inflation is correct, it naturally leads to a multiverse of bubbles. Testing inflation, by studying the patterns in the microwave background, or by searching for primordial gravitational waves, is one way of testing the roots of the multiverse idea. We may never see another bubble directly, but we can strengthen or weaken the theory that predicts them. Quantum many worlds poses a different challenge. Every experiment we run in the laboratory works equally well in the many worlds interpretation and in the traditional interpretation where probabilities collapse. The difference is philosophical. Do all outcomes exist, or only one? For now, no experiment can tell. That does not mean the idea is meaningless, but it does mean it sits on the border between physics and interpretation, between evidence and worldview. And then there is the mathematical multiverse, where every possible structure exists. By its very nature, this version resists testing. If all things are real somewhere, then no single experiment can prove or disprove it. It becomes a perspective on existence rather than a falsifiable hypothesis. Some scientists welcome it as a profound insight. Others set it aside as beyond the bounds of science. This tension between what we can measure and what we can only imagine is not new. Centuries ago, people debated whether atoms were real. No one could see them directly, and yet the idea explained chemical reactions in elegant ways. It took generations before microscopes and experiments confirmed the atomic picture. Perhaps the multiverse is similar, a powerful idea that may one day find unexpected evidence. Or perhaps it will remain forever untestable, a story we tell to stretch our minds. To soften the abstraction, think of standing before a mountain range shrouded in mist. You cannot see the peaks beyond, but you can see rivers flowing down, shaped by hidden contours. From the rivers, you can guess at the mountains, even if you never climb them. In the same way, cosmologists look for indirect flows of evidence, patterns in the sky, distributions of galaxies, ripples in ancient light that might hint at realities beyond sight. But there is another perspective to hold gently. Science is not only about answers, it is also about the questions that shape our curiosity. Even if the multiverse remains forever out of reach, thinking about it sharpens our sense of what space and reality could be. It reminds us that universe may not mean everything, but only everything we can observe. And that distinction alone reshapes how we think of our place in the cosmos. This is why some scientists treat the multiverse not as a final theory, but as a heuristic, a guide to thought. It keeps us from assuming that our observable patch is the whole of existence. It encourages humility. It whispers that the cosmos may be richer than we can ever confirm, and that our maps will always be incomplete. Everyday life offers a similar lesson. Think of stories told around a fire. Some are about known lands with mountains and rivers you can point to. Others are legends of distant places, never visited, perhaps never real. Both kinds of stories matter. One grounds you, the other expands your imagination. The multiverse belongs for now to the second category. It may someday move to the first, but even if it never does, it teaches us to see our universe not as the whole, but as a chapter in a story too vast to close. As we let this thought drift, our path now carries us forward, not into speculation, but into destiny. If our universe continues to expand, shaped by dark energy and stretched by time, what future awaits? Does space go on swelling forever, cooling into emptiness? Does it tear itself apart in a catastrophic rip? Or does it fade into a heat death, where all distinctions blur into stillness? Our quiet exploration now turns to the fate of space itself, where the far future beckons with scenarios both haunting and strangely serene. So far, we have wandered through the story of beginnings, the glow of the baby universe, the stretching of inflation, the patterns that seeded galaxies. But every story has not only a past, but also a future. What will become of space itself in the long run? Will the balloon keep expanding forever? Will it slow and collapse? Or will it tear apart in something stranger still? The fate of space is written in its expansion. We know today that the universe is expanding, and not just at a steady pace, but with acceleration. Galaxies are drifting farther apart, faster and faster, carried outward by dark energy. But how that expansion unfolds across billions and trillions of years depends on the nature of that dark energy, something we do not yet fully understand. Scientists imagine several possibilities, each with its own quiet poetry. The first is called the Big Freeze, sometimes called heat death. In this future, dark energy continues to drive expansion forever. Galaxies grow so distant that their light no longer reaches one another. Stars burn out, one by one, until the night sky goes dark. White dwarfs cool into black husks, neutron stars fade, black holes slowly evaporate by releasing faint radiation. In the end, all that remains is a thin soup of particles drifting in a cold, silent universe. No fire, no galaxies, only a uniform stillness. It is like a campfire that has burned to ash, leaving only cold air behind. Another possibility is the Big Rip. If dark energy grows stronger with time, its push may not remain gentle. Instead, it could increase so much that eventually it tears galaxies apart, then stars, then planets, and finally even the atoms themselves. The very fabric of space-time would be ripped to shreds. This is a more violent ending, like stretching a balloon until it bursts. Whether the universe ends this way depends on whether dark energy's strength is truly constant, or if it changes with time. For now, observations suggest it may be constant, but we cannot be sure. A third option is that expansion continues forever but asymptotically, approaching stillness without collapse. In this version, the cosmos drifts gently toward emptiness, not with a bang or a tear, but with a slow fading. Imagine a candle burning in a quiet room. The flame grows smaller, then flickers out, leaving only smoke. That is the quiet end of heat death. Not destruction, but dissolution. There was once another possibility, now mostly set aside by evidence, the Big Crunch. If gravity was stronger than dark energy, expansion would eventually slow, stop, and reverse. The universe would collapse back in on itself, galaxies rushing together, stars colliding, heat and density rising until everything returned to a fireball. It would be as though the cosmos inhaled after a long exhale. Today, data suggests this is unlikely since dark energy dominates. But the thought of a cyclical universe with endless bangs and crunches still stirs the imagination. To bring these scenarios closer, let's anchor them in everyday images. The Big Freeze is like a campfire where the last ember cools into darkness. The Big Rip is like a balloon stretched beyond endurance, snapping apart. The Big Crunch is like a ball thrown upward, slowing, then falling back into your hands. Each picture carries its own mood, serene, violent, or cyclical. What unites them is the reminder that space is not static. It evolves. The fate of the cosmos depends not only on its contents, but on the hidden nature of dark energy. If dark energy is truly constant, the Big Freeze seems most likely. If it grows, the Big Rip awaits. If it fades or changes, who knows what future lies ahead? And yet, there is a strange comfort in all of these stories. They take place on timescales so vast that they make even the oldest galaxies seem young. Stars live billions of years, but these fates play out over trillions, quadrillions, even longer. The numbers slip beyond comprehension. Compared to them, the entire history of human civilization is less than a blink. This vastness does not diminish our moment. It magnifies it. We live during a rare era when the sky is rich with galaxies, when the night is still bright with stars. Far in the future, the view will grow emptier. Observers may no longer see the cosmic microwave background. They may not know of the wider universe at all. We, in this narrow window of cosmic time, are privileged to witness it. Think of it like standing by a fire just as the flames are highest before they fade. The warmth on your skin is brief, but unforgettable. Humanity exists in a similar glow. The glow of a cosmos still filled with light, still revealing its secrets. Our moment may be temporary, but it is luminous. In the end, whether the universe freezes, rips, crunches, or fades, space itself continues to remind us of impermanence. Everything changes. Stars die, galaxies drift, horizons shift. Yet in the midst of this change, life arose, eyes opened, and minds wondered. That fact alone makes the fleeting glow worthwhile. As we let these visions of the far future settle, our quiet path now carries us to a gentle reflection. If the universe may be infinite, or finite but without edges, if it may end in silence or in fire, what matters most for us here and now? Our exploration turns toward living with our horizon, what it means to exist in a cosmos so vast, and how curiosity and wonder can be our constant companions, even when answers remain incomplete. We have journeyed far, back to the baby universe glowing softly at 380,000 years of age, through the sudden burst of inflation, across the ballooning fabric of space, and even into the speculative realms of bubbles, domains, and holograms. We have looked ahead into deep futures where stars fade or the very fabric of space might tear apart. Now, as we come to rest, the question remains, what do we do with all of this knowledge? How do we live, knowing our cosmos may be infinite, or finite yet unbounded, or destined to fade? Perhaps the most important lesson is that space does not need walls. The cosmos may be vast without edges, finite without borders, infinite without limit. Our horizons are not barriers but boundaries of vision. They mark how far light has carried news to us, not where reality itself stops. Just as a sailor gazing across the ocean sees the horizon as a circle, yet knows the sea extends further, we too must learn to treat our cosmic horizon as the limit of our sight, not the edge of existence. There is humility in this. For thousands of years, humans imagined themselves at the centre of Earth, of the solar system, of the universe. Each time we learned otherwise. Copernicus showed us Earth was not the centre of the planets. Galileo's telescope revealed countless stars beyond the naked eye. Hubble's measurements showed galaxies far beyond the Milky Way. And now, modern cosmology shows us that even the universe we see may be only a patch in a greater quilt, one bubble in a greater foam. With each discovery, our centrality shrinks, but our wonder grows, and wonder is the key. If the universe is infinite, then every direction holds endless possibilities. If it is finite yet unbounded, then it is a masterpiece of geometry, a canvas without edges. If it will end in heat death, then our era of stars is a rare and precious glow. If it will rip apart, then our moment is an oasis of calm before unimaginable change. In each case, the fact of our existence, that atoms became stars, stars forged heavier atoms, and those atoms formed living beings capable of asking questions, remains the miracle. Everyday anchors can help us carry this home. Think of a map. The map is never the territory, it is always smaller, always incomplete. Yet we rely on it to navigate. Science gives us maps of the cosmos, expansion, geometry, horizons. But these maps are not the whole. They are sketches of what we can see, drawn with the best tools we have. Beyond the edges, blank spaces remain. Like old maps labelled "Here be dragons," our cosmic charts remind us of the unknown. Instead of dragons, we write inflation, dark energy, or multiverse. The names change, but the mystery remains. Or think of the ocean. Stand at the shore and look out to sea. The horizon is clear, a line dividing water and sky. Yet you know the ocean continues beyond, curving with the earth. The horizon is not the end. It is the point where your sight bows to distance. The universe is like that. Our cosmic horizon, at about 46 billion light-years in radius, is not an end. It is simply where light has not yet reached us, where time has not yet allowed a message to arrive. Beyond it, the ocean of space continues, calm or stormy, unseen but real. There is also a gentleness in accepting limits. We may never know whether space is truly infinite. We may never see beyond our horizon. But perhaps that is part of the gift. Limits invite imagination. They keep us humble. They remind us that science is not about owning the answers, but about refining the questions. To live with our horizon is to live with curiosity, to let the unknown be not a threat, but a companion. And so, we return to ourselves. Whether the universe is endless or looping, whether it ends in fire or silence, what matters most is that we are here now, listening to the hum of existence. You are breathing air shaped by stars that died billions of years ago. You are made of atoms forged in stellar furnaces. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it comes from a cosmos that began in fire and expanded into possibility. You're not separate from the story. You are the story, told for a moment in the shape of a human being. As this journey closes, let us rest in the style of the Sleepless Scientist, with gratitude and calm wonder. Hello there, and thank you for wandering so far tonight. You've travelled with me from the newborn glow of the cosmos to its possible endings, through bubbles, balloons, and horizons that stretch beyond sight. And now, whether your eyes are still open or already heavy, whether your thoughts are clear or drifting like leaves on a stream, know that you are part of this grand unfolding. Space may or may not end, but wonder does not. If you'd like to join again for another quiet journey, you are always welcome here. Subscribe if you wish, or share this with someone who might need a moment of calm. For now, let the questions soften, like embers fading at the edge of a campfire. Let curiosity rest beside you, not demanding answers, but offering companionship. Space stretches, time flows, stars are born and fade. But in this moment, you are here, listening, breathing, and safe. Sleep peacefully wherever you may be, beneath the vast and gentle sky.